This is a passenger cargo steamship from over 100 years ago. A dual-purpose steamship for both passengers and cargo. Its layout is quite interesting. The most stable and comfortable position on the ship is the first-class cabins. The massive cargo holds are like a sandwich, tightly sandwiching these first-class areas in the middle. The second-class cabins are distributed in the remaining space outside the cargo holds, and the most basic and noisiest section at the stern belongs to the third-class cabins. Going further down, we enter the lower levels of the ship. This is the power system of the entire ship. 6 coal-fired boilers are arranged in 2 rows facing each other. The flue gases from coal combustion are collected through the flues and exhausted through the main chimney. Behind the boiler room is connected to the engine room. Inside are installed 2 4,000 horsepower steam engines. The power is transmitted through the drive shaft, extending all the way back, driving the ship's 2 counter-rotating propellers. We will mainly focus on the power section of this ship. The entire ship has a total of 6 coal-fired boilers. Each single boiler is 4.6 meters high. It vertically spans several decks. It is surrounded by huge coal bunkers. The boiler is fixed to the hull structure through raised floor brackets. Each boiler is equipped with 3 furnace doors. The firemen need to evenly shovel coal into the firebed to ensure complete combustion. Next, the hot gas flow from coal combustion first enters the rear combustion chamber, then rises upward through rows of smoke tubes at the top. Water is distributed around the smoke tubes. As the hot gases pass through, they first transfer heat to the water, generating steam at the top of the boiler. Then this high-pressure steam is transported through the main steam piping to the main engine. Like the boiler, it spans multiple decks. When the steam produced by the boiler reaches the engine, it is first controlled in total volume by the main throttle valve. Subsequently, the steam enters the valve chest, inside which there is a piston valve moving up and down, responsible for controlling the intake timing of the high-pressure cylinder. When the valve opens, high-pressure steam rushes into the cylinder, pushing the piston downward to do work. When the valve closes, the exhaust port opens, and the steam that has completed its work is exhausted out. The valve and piston operate alternately in synchronization, and the engine continues running like this. This steam engine is of a double-acting design. You can see that both above and below the piston have intake and exhaust ports. The structure is symmetrical top and bottom. Fresh steam can push the piston downward or enter from the bottom to push it back up. One complete round trip is a full working cycle. The entire engine has a total of 4 groups of such cylinders, adopting 4-stage expansion technology. High-pressure steam first enters the smallest diameter high-pressure cylinder, then sequentially passes through 2 intermediate pressure cylinders, and finally enters the largest low-pressure cylinder. The cylinders are arranged from small to large, perfectly matching the trend of steam pressure decreasing step by step, extracting every last bit of energy. When the steam has finished doing work, it leaves the engine and enters the condenser to turn back into water. Due to the high-pressure power system having particularly high requirements for water quality, seawater cannot be used, so every drop of condensed water generated during navigation must be recovered and recycled. The condensation process here is completed entirely by a steam-driven centrifugal pump. First, it draws in low-temperature seawater from outside the ship, which flows through rows of small tubes in the condenser. The exhaust steam from the engine contacts these icy tube walls and condenses into water, accumulating at the bottom. At the same time, the engine also drives an air pump to draw out the air in the system. When water vapor condenses into water, the volume shrinks 1,600 times. This creates a vacuum suction that can suck the exhaust gas from the cylinders more cleanly. The piston in the low-pressure cylinder naturally works with higher efficiency, but this is only the first step of the cycle. The condensed water then flows through a condensate filter to separate out the mixed-in lubricating oil, ensuring the water is clean before being sent back to the boiler. Before that, the water enters the contact heater to mix directly with the exhaust steam discharged from other equipment on the ship for preheating in advance. The water temperature rises directly from 60 degrees Celsius at the outlet to nearly boiling 90 degrees Celsius. This way, when re-entering the boiler, it won't cause thermal stress from cold water shock. At the same time, the heater uses its elevated installation layout, relying on gravity to vent the air bubbles in the water into the venting system so that bubbles in the high-pressure piping won't cause cavitation damage. Finally, the main feedwater pump will, as needed, pump the treated water back into the boiler. This is a modern, large-scale bucket-type grain silo system. It processes freshly harvested grain all the way to finished grain that is ready for storage and outward transport. What processes does it go through in between? Let's take a look together, starting from the grain unloading stage. Grain trucks park right above the pit. The grain falls by its own weight directly through the grid plate at the unloading port and drops into the bottom pit. Below the pit is a scraper-type conveyor. Chains drive the scraper plates inside a fully sealed channel to smoothly push the grain out. The grain then enters the bucket elevator inside the red tower. This elevator works like a vertical lift. High-speed circulating buckets lift the grain dozens of meters into the air. At the top, centrifugal force throws it into the discharge pipe. It then enters the core cleaning stage. The purpose of this stage is to quickly remove high-moisture impurities and prevent the grain from molding. To handle large-scale throughput, some facilities use this cylindrical cleaning sieve. The rotating cylinder tumbles the grain while multi-layer screens precisely sort it. Straw and stones exit from the end, while light husks and chaff are vacuumed away by negative pressure airflow. This tumble and suction system ensures extremely high purity of the incoming grain. Of course, cleaned grain isn't stored long-term right away. It's first diverted at the top of the tower and sent through a discharge pipe into an adjacent metal buffer silo. This acts as a buffer because harvesting and transport happen very fast, while processing steps are slower. So the silo serves as a transfer station. It temporarily holds high-moisture grain and releases it in controlled batches. Next comes the core drying stage. Depending on grain type and scale, there are two main drying methods. The first is this vertical continuous drying tower. Grain slowly falls from the top like a waterfall by gravity. Fans at the bottom draw in ambient air and heat it to 40–60 degrees Celsius. Hot air penetrates the grain layer in stages, carries away moisture, and exits as humid air. This method offers massive throughput and is ideal for corn and other grains that need rapid moisture reduction. For grains requiring more precise moisture control, a circulating dryer is used. A bucket elevator repeatedly lifts the grain to the top so it evenly contacts hot air multiple times during circulation. This slower, more careful process effectively prevents cracking or breakage from rapid dehydration. It ensures the highest quality finished grain. After drying, the grain enters a multi-layer vibrating cleaning sieve to remove any remaining impurities and broken kernels. It is then sent to the elevated bulk loading bay. Once the truck is in position, loading begins. For long-term storage, grain meeting drying standards is sent into silver corrugated finished silos. Through an elevated conveyor bridge and a rotating distributor inside the silo, grain is spread evenly to avoid compaction. Fans on both sides work with bottom air ducts to circulate dry air evenly through the pile and slowly regulate moisture and temperature. When it's time for transport, the central rotating sweeper scrapes all grain toward the central discharge outlet and the bottom conveyor efficiently removes it. This achieves fully automatic, residue-free discharge. The entire process is enclosed and highly efficient. Of course, besides fixed drying towers in large facilities, there's also this more flexible mobile dryer. It can be towed directly to the field to dry freshly harvested grain on site. Dried grain is discharged straight into trucks through a pipeline, no extra handling needed. It's especially suitable for small farmers and family farms from unloading to cleaning, drying, storage, and transport. This fully automated process is both efficient and standardized. It enables safe, large-scale grain storage while flexibly meeting drying needs in any scenario. I used to think that the sharper an icebreaker's bow was, the more powerful it had to be. But after learning how icebreaker technology evolved over time, I realized that idea was completely wrong. In fact, the most advanced icebreakers in the world actually have blunt, heavy, rounded bows. In the polar oceans, where temperatures fall far below freezing, ice sheets can easily become 1 or even 2 meters thick. Ordinary ships can't move through ice like that. Most of them can't even move at all. More than a century ago, early icebreakers were designed with sharp bows, almost like giant knives. They worked fine on thin ice, but the moment the ice became thicker, the ships got stuck instantly. Crews often had to climb out with axes and manually chop the ice apart. It was slow, exhausting, and extremely dangerous. Everything changed in 1871 when a German engineer realized something revolutionary. Ice doesn't need to be cut, it needs to be crushed. That discovery completely changed icebreaker design. Engineers abandoned the sharp bow and replaced it with a thick, rounded, downward-sloping shape. Instead of smashing directly into the ice, the ship would climb up onto the surface and use its enormous weight to crack the ice underneath. But this new design created another problem. These ships consumed huge amounts of fuel, and because they sat relatively high in the water, a fully loaded vessel would sink lower, causing the bow to dip underwater. Once that happened, the ship could no longer climb onto the ice effectively, and its ice-breaking advantage disappeared. So engineers kept refining the design. They extended the bow and carefully adjusted its angle, making sure the ship could maintain the perfect ice-breaking position, whether lightly loaded or carrying maximum cargo. Only then did icebreakers become truly reliable machines capable of continuous operation. However, early icebreakers still relied on diesel engines. In the harsh and isolated polar regions, fuel quickly became a major limitation. A single long expedition could end in disaster if supplies ran out. Then, in 1957, everything changed again with the launch of the world's first nuclear-powered icebreaker. Using nuclear fission, the ship could generate massive amounts of heat continuously. Water was converted into high-pressure steam, which drove powerful turbines connected to the propulsion system. This technology allowed an icebreaker to operate in polar regions for 3 to 4 years without refueling, reaching some of the most remote frozen areas on Earth. That already sounds impressive, but the Arctic environment is even more brutal than most people imagine. When an icebreaker crashes through thick ice at high speed, massive chunks of broken ice slam back against the hull. Some of them can even damage the propellers and rudder. And if those critical parts fail, the entire ship becomes helpless. To solve this, engineers added auxiliary propulsion systems along both sides of the ship. These systems create powerful water turbulence that pushes nearby ice away from the hull, protecting the main propellers from damage. But another issue still remained: friction. The constant grinding between steel and ice slowed the ship down and gradually wore away its structure. Engineers reinforced the hull with stronger internal steel frameworks and added heavy steel belts along the sides to improve impact resistance. Then came another brilliant innovation. Engineers began mixing seawater with air and releasing it beneath the ship, creating a dense layer of bubbles around the hull. This invisible bubble layer acted like a lubricant, separating the steel from the ice and dramatically reducing friction. At that point, icebreakers no longer needed to force their way through the ice. They could practically glide across it. And this is when icebreakers truly evolved into giant polar engineering machines. Among them, one of the most impressive is China's independently developed Shuilong 2. It pushed ice-breaking technology to an entirely new level. Not only can it break ice moving forward, it can also break ice while moving backward. Even more impressively, it can rotate 360 degrees in narrow ice fields, allowing it to perform highly complex operations in some of the harshest environments on Earth. I've always been curious why a forklift has such a short wheelbase, yet it can still lift several tons of cargo. Today, in this video, I'll explain the mechanical logic behind every single forklift movement. After watching this, you'll understand it like a pro. The reason this machine can lift several tons of weight and precisely place the load anywhere with just one control lever lies in its internal, extremely powerful hydraulic system. The core principle is Pascal's law. Two pistons are connected inside the same sealed chamber filled with hydraulic oil. A small input force on the small piston is transmitted through the hydraulic system and produces a massive output force on the large piston. Every lift, tilt, and side shift movement on a forklift is based on this principle. Now that we understand the basic hydraulic principle, let's look at the key components inside the forklift. The first is the hydraulic pump. It drives the entire system by sucking hydraulic oil from the tank and pumping it into the hydraulic lines. But remember, the pump itself only creates flow. It pushes oil from low pressure to high pressure. The actual working pressure is only generated when you lift a heavy load or adjust the mast angle and the oil flow meets resistance. Next is the control valve. It decides which path the high-pressure oil should take. As soon as you move the corresponding control lever, the internal valve opens and high-pressure oil rushes through the lines into the specific hydraulic cylinder to drive the lift, tilt, or side shift movement. The type and speed of the movement depend entirely on which valve you open and how far you open it. Next is the hydraulic oil. This specially formulated industrial oil is chosen to meet multiple critical requirements: transmitting pressure, lubricating moving parts, and cooling the entire system. Finally, the hydraulic cylinders. This is where fluid pressure is converted into actual mechanical movement. A standard forklift usually has lift cylinders to raise and lower the mast, tilt cylinders to adjust the mast angle forward or backward, and side shift cylinders for left, right fork movement, and rotation. When high-pressure oil enters a cylinder, there is a piston inside connected to a piston rod. The pressurized oil acts directly on the entire surface of the piston. The force pushes the piston to extend or retract, producing lift, tilt, or side shift movement. Now that we understand these core components, let's follow the complete hydraulic cycle from the moment you move the control lever. When the engine starts, the hydraulic pump begins working, sucking oil directly from the tank. The oil flows through the suction pipe and through the pump gears toward the control valve block. But as long as you don't move the control lever, no pressure builds up in the system. The oil simply circulates through the valve group and returns to the tank at low pressure, on standby. Now, when you pull the lift lever, it breaks this idle state. The spool inside the control valve instantly slides to a new position. This closes the return oil passage and opens a dedicated channel, directing the high-pressure oil from the pump straight into the lift cylinder's inlet port. At this moment, oil enters the lower chamber of the lift cylinder through high-pressure steel pipes and pushes against the entire surface of the piston. As the piston moves, the connected piston rod pushes upward. In this way, the forks and cargo rise smoothly. When you release the lever, it springs back to neutral. The spool immediately returns and blocks the oil path, trapping the high-pressure oil inside the lift cylinder. This firmly holds several tons of cargo in place. If you want to lower the load, push the control lever forward. The spool shifts again, opening a direct return path to the tank. The oil from the lower chamber of the cylinder flows back through the valve body, but first it must pass through a built-in flow regulator. This regulator's job is to strictly control the oil flow rate, preventing several tons of cargo from crashing to the ground. You see, when oil flows out from the lower chamber, the piston moves downward. The piston rod retracts into the cylinder, and the cargo and forks lower smoothly under their own gravity. This is a complete standard hydraulic lift cycle. Now, let's see what happens when you operate lift and tilt at the same time. This is where the hydraulic system really shows its precise control. When you grab both the lift and tilt control levers and pull them at the same time, the hydraulic valve block immediately takes over and intelligently distributes the limited oil flow. Most forklifts are programmed to prioritize flow to the lift circuit. So even while you're tilting the mast backward, the system still maintains full pressure to the lift cylinders, keeping the forks rising steadily. At the same time, the control valve smoothly diverts a small portion of flow to the tilt cylinder. The tilt movement may not be as fast as when operated alone, but it remains perfectly smooth and responsive with no jerking or hesitation. This is why experienced operators can lift a pallet upward while simultaneously tilting the mast backward, and the entire forklift stays completely stable with no shaking. That's the basic mechanical logic of forklift operation. Did you get it? I've always been curious about something. How can a plane weighing hundreds of tons land at such incredibly high speed? And how exactly does it manage to come to a complete stop within just 30 seconds? Many people think that when a plane lands, it just touches down with a thud, and then the pilot simply steps on the brakes. But it's not that simple at all. Because before the wheels even touch the ground, they are actually completely stationary. Yet the plane itself is still hurtling forward at nearly 300 kilometers per hour, charging ahead at full speed. This means that the moment the tires touch the ground, they must go from completely still to nearly 300 kilometers per hour in less than 1 second. This kind of insane acceleration would destroy ordinary car tires instantly. So if landing is so dangerous, why not spin the wheels up in advance? Well, if the tires were locked up and touched down early, the massive friction would shred them in an instant. In severe cases, it could even cause fire and explosion. So the real problem engineers must solve has never been how to brake, but how to make the wheels touch down safely. That's when you'll discover that the plane's true first deceleration system isn't the brakes at all, it's the air. When the plane is preparing to land, the landing gear is lowered early. The spoilers on the wings, which were flush before, suddenly deploy upward. Many people think these are just routine actions, but they're actually creating massive drag on purpose, because the faster the plane flies, the greater the air resistance becomes. Engineers use this principle to let the air help slow the plane down early. But air resistance alone is far from enough. A large airliner can weigh hundreds of tons, and air resistance by itself could never stop it on a finite runway. So here's the second problem: how to make the tires brake effectively without blowing out on impact. The truly difficult part happens at the exact moment the wheels touch down. Because the tires don't spin up by themselves, they're violently forced to rotate by the ground. In that split second, the impact force on the tires is extreme. That's why the landing gear isn't just a few support struts. It's more like a giant hydraulic shock absorber. When the plane touches down, the entire fuselage slams down hard. But inside the landing gear, hydraulic oil and high-pressure nitrogen act like a giant spring, absorbing the massive impact bit by bit. But shock absorption is only the first step. What really decides if the plane can stop is the carbon brake system in the wheels. It works on a similar principle to car brakes. When the pilot applies the brakes, hydraulics push a stack of carbon fiber discs to clamp the wheel tightly. The tires then grind fiercely against the runway, and the plane starts decelerating rapidly. But if you brake too aggressively, the tires will lock up and skid. And once skidding begins, it becomes extremely dangerous. Because when the tires skid, friction drops dramatically. Not only will the plane fail to stop, it could also veer off the runway. So what do? Engineers invented another incredibly advanced system, the anti-skid braking system, basically the airplane version of ABS. And every single wheel has its own independent speed sensor, which monitors each wheel's rotation speed in real time. Because if one side brakes too hard, the whole plane could be pulled off course. The system constantly compares the aircraft's actual ground speed with each tire's rotational speed. If it detects a wheel slowing down too fast, it knows that wheel is about to blow out. So the system instantly releases brake pressure slightly, lets the tire start spinning again, then reapplies pressure. This process repeats dozens of times per second. That's why many people think the pilot is frantically pumping the brakes after landing. But in reality, what's working overtime is the sophisticated automatic control system behind the scenes. But do you think that's the end? Not even close. Because for a hundreds of tons airliner, wheel brakes alone are still not enough. It also needs engine reverse thrust. Normally, the engines blast air backward to push the plane forward. But after landing, the engines suddenly reverse the airflow, turning backward thrust into forward thrust, essentially pushing the plane backward. That loud roaring sound you hear after touchdown is often the reverse thrust system working at full power. So you'll see that a plane's true deceleration is never done by any single system alone. It's the combined effort of air resistance and spoilers, hydraulic shock absorption, carbon brakes with anti-skid system, and engine reverse thrust, all working together perfectly. Because for an airplane, the hardest part has never been taking off. It's safely stopping this hundreds of ton steel giant after a high-speed sprint. So do you still think that landing a plane is just stepping on the brakes? I've always thought that seamless steel pipes are just made by taking an iron pipe, stretching it and polishing it, and that's it. Until I saw the actual production site for the first time, I realized this thing isn't made at all. It's literally pushed out by force. First, a solid round steel billet, tens of centimeters thick, is sent into a heating furnace. The temperature skyrockets to over 1,000 degrees. It slowly heats up until it's glowing red hot. At this point, the billet is no longer the hard metal you imagine. It's more like a huge chunk of soft, sticky Play-Doh. Next, the scorching hot billet is clamped by two massive sets of rollers. They spin at high speed while forcefully pushing it forward. Note this, there's no drill bit in front. What actually pierces through it is a fixed mandrel in the middle. Just imagine, two powerful forces outside twisting and squeezing it like crazy, while a sharp tip inside stubbornly resists. The internal pressure instantly becomes unbalanced. The solid center cracks open first from the extreme tensile force. This is the famous skew roll piercing process. In just a few seconds, a solid steel billet has a hole punched straight through the middle. But it's not that simple. Right after piercing, the hole inside is very rough, with uneven thickness, a bumpy surface, and even eccentricity. If you tried to use it under high pressure right away, the entire pipe could explode. That's why it goes through the most critical step, mandrel rolling. A long, precisely sized mandrel is inserted into the steel pipe. At the same time, the outer rollers keep squeezing hard from the outside, while the mandrel supports from the inside. The steel pipe is forced to stretch along its length. The originally thick and short billet gets pulled longer and longer, and thinner. The whole process looks a lot like rolling dough, except you're not rolling dough. You're rolling steel at over 1,000 degrees. But here's a problem. As the pipe gets stretched longer, sometimes up to dozens of meters, how is that mandrel inside fixed? Won't it just move around with the pipe? Actually, most mandrels aren't fixed at all. Some are held by an extremely long mandrel rod from behind, while others are floating mandrels. A floating mandrel isn't locked in place. It stays centered thanks to the friction from the fast-moving pipe, the metal flow force, and the pressure difference between front and back. It automatically stays in the middle. In simple terms, as the pipe shoots forward, the mandrel gets carried along at just the right angle by the flowing metal. But its speed, position, and angle must be controlled with extreme precision. If it deviates even slightly, the pipe wall thickness becomes uneven, and the whole pipe is scrapped immediately. So, you'll notice, seamless steel pipes may look like they're being violently processed, but the real challenge isn't the force, it's the control. After that, the pipe still goes through alkali cleaning, sizing, cooling, and straightening. Dozens of rolling stands take turns squeezing it, fine-tuning the dimensions bit by bit. Finally, it undergoes ultrasonic flaw detection and hydrostatic testing to catch any internal cracks. Only then is a truly qualified seamless steel pipe born. So, don't be fooled by its ordinary-looking exterior. Behind it lies extreme high temperatures, dozens of tons of continuous pressure, and ultra-precise control all working together to create this industrial monster. What's even crazier is that many deep-sea pipelines and high-pressure boilers in nuclear power plants, what really determines their safety might just be this one seemingly ordinary steel pipe. Now you know how seamless steel pipes are actually hollowed out. I always thought a drilling rig was just a giant version of an electric drill. You just point it at the ground, go brr brr brr, and it's done. But I never expected that real industrial drilling doesn't rely on rotation at all. Instead, it relies on hammering the rock more than 2,000 times per minute, smashing it bit by bit to drill downward. Sounds pretty interesting, right? Today, I'm going to use 3D animation to show you exactly how modern shallow-hole drilling rigs work. This type of rig can drill as deep as 25 kilometers underground. Its core power source isn't electricity, it's compressed air, with pressure reaching up to 4,500 pounds per square inch. As soon as the engine starts with a loud roar, it drives the compressor. Air gets sucked in and is compressed wildly all the way from loose, soft gas into an extremely powerful high-pressure airflow. This air is then sent straight down through the drill pipe, which acts like a long, hollow tube delivering all that force directly to the very front underground. But high-pressure air alone can't break hard rock, so engineers turned that air into a hammer. Next to the rig sits a 400 to 500 horsepower engine equivalent to the power of 3 or 4 off-road vehicles all packed inside an iron box. It drives a screw rotor at high speed, compressing the air tighter and tighter. However, while the air is being compressed, its temperature rises sharply. If the gas gets too hot, the pressure becomes unstable and the force actually decreases. That's why a complete high-power cooling system is installed at the outlet of the high-pressure unit. It forcibly cools down the scorching hot air, so the pressure can stay steady. The cooled high-pressure air is then sent underground. It first rushes into the space above the piston, violently pushing it downward. The piston slams hard onto the hammerhead, which transfers the massive force straight into the rock. At the exact moment of impact, the air path automatically switches. High-pressure air now rushes to the bottom of the piston, pushing it back upward. Down, up, down again. The whole process cycles completely automatically, completing between 1,000 and 2,500 impacts every minute with no one controlling the rhythm. It purely drives itself using air pressure. At the very front of the hammerhead, there's a ring of carbide teeth embedded. This material is insanely hard and specifically designed to withstand these high-frequency, brutal impacts. If the hammer just kept smashing the same spot, the rock would only get a deep pit, and efficiency would be extremely low. It might even get stuck. So while the drill is hammering, it's also slowly rotating. With each smash, the angle shifts just a tiny bit, so the next hit never lands in the same position. This way, impact handles breaking the rock, while rotation handles clearing it, finally forming a perfect round hole. But as it drills deeper and deeper, crushed stone, mud, sand, and rock powder pile up at the bottom of the hole, burying the hammerhead. Once buried, the impact force gets completely absorbed by all this debris. It's like hammering for nothing. So after every impact, the excess high-pressure gas isn't wasted. Instead, it sprays out at high speed from small holes on the side of the hammerhead, forming a powerful airflow that blows the crushed rock upward from the hole bottom. These debris travel along the gap between the drill pipe and the hole wall, getting carried all the way up and shooting out of the ground at an angle. So the grayish-white dust you constantly see spraying from the ground isn't a leak, it's automatic debris removal in action. However, if the rig encounters an especially hard rock layer, hammering alone still isn't enough. The drill bit might even slip in place and stop moving downward. That's when the hydraulic system kicks in. The hydraulic pump at the top of the tower, through a pulley mechanism, applies downward pressure to the entire drill string, pressing several tons of weight directly onto the hammerhead. Combined with the pneumatic impact, this double force makes even the hardest rock layers start to break apart. Finally, when the well reaches the target depth, the impact stops. But the high-pressure air doesn't stop, it keeps working, blowing all remaining debris from the well bottom completely clean until the entire well bore is thoroughly formed. So, what you're seeing now with this drilling rig isn't drilling at all. It's simultaneously performing three things underground: impact, debris removal, and advancement. And it also has to constantly control temperature, pressure, and direction. If any single link goes wrong, the entire well will be scrapped immediately. So the big question is, what if there's no compressed air? Can this kind of drilling rig still work? Have you ever wondered how a heavy truck weighing dozens of tons can be brought to a complete stop by just a small amount of force from the driver's foot? It seems almost impossible, yet it produces incredibly powerful braking force. In reality, the driver isn't stepping directly on the brakes themselves. Instead, they are controlling a powerful force of compressed air. This is the most common air brake system found on heavy trucks today. Many people think that air brakes are the actual braking mechanism, but that's completely wrong. Air brakes do not directly create the friction needed to stop the wheels. Their only job is to control and activate the braking system. What actually stops the vehicle is the drum brake assembly located inside each wheel. If you open up a truck wheel, you will see two curved brake shoes pressed tightly against a large brake drum. When these shoes are pushed outward, they clamp firmly against the inner wall of the drum, instantly generating strong friction that quickly halts the wheel's rotation and slows down the entire truck. The component responsible for pushing the brake shoes apart is a special-shaped cam. As this cam rotates, it forces both brake shoes open at the same time, making them grip the drum tightly. This cam is connected to a sturdy metal push rod. The moment the push rod moves forward, the cam turns, the shoes open, and the brakes engage. With enough force applied to this push rod, the truck can generate extremely powerful braking force, and that's exactly what the air brake system is designed to do. The power source for the entire air brake system comes from an air compressor mounted next to the engine. This compressor is belt-driven by the engine. As long as the engine is running, it continuously sucks in outside air and compresses it to very high pressure. This compressed air is then stored in the vehicle's air reservoir tanks. However, during the compression process, the air often picks up moisture, dust, and impurities. If these contaminants enter the brake system, the entire braking mechanism could fail. That's why the air must first pass through an air dryer before entering the reservoir. The dryer removes all moisture and pollutants, keeping the air inside the tanks dry, clean, and stable. This ensures the air brake system always has a reliable power source. But air cannot be compressed forever. If the pressure keeps rising without control, the system could explode. To prevent this, A pressure regulator is installed to carefully control the air pressure. On most trucks, the air brake system operates between 0.6 and 1 megapascals. When the pressure in the reservoir reaches about 1 megapascals, the diaphragm inside the regulator is pushed upward, automatically closing the intake valve and stopping the compressor. When the pressure drops back down to around 0.6 megapascals, the diaphragm returns to its original position, reopening the intake and allowing the compressor to start charging again. This continuous cycle keeps the entire system within a stable and safe pressure range. Once the air system is ready, control is handed over to the driver's foot. Beneath the brake pedal in the cab lies the core component, the brake valve. When the driver presses the pedal, it pushes a piston inside the valve downward, opening the air circuit and allowing compressed air from the reservoir to flow rapidly through the lines. The lighter you press, the smaller the valve opening and the less air flows. The harder you press, the wider the passage opens and the stronger the airflow becomes. In other words, the driver isn't stepping on brake pads, they are precisely regulating the flow of high-pressure air. However, if all the air had to travel from the cab all the way to the rear of the truck through dozens of meters of piping, the brake response would be too slow. To solve this problem, engineers added a relay valve. When the brake signal is sent, the relay valve doesn't send the air the long way around. Instead, it opens a direct, large passage, releasing high-pressure air from the nearby reservoir straight into the brake chamber. Inside the brake chamber is a large rubber diaphragm. When high-pressure air enters, the diaphragm bulges outward, creating a powerful thrust that immediately pushes out the pushrod. The pushrod then rotates the S-cam, causing the two brake shoes to snap open and clamp tightly onto the brake drum. In just a fraction of a second, a truck weighing dozens of tons is brought to a firm stop. When the driver releases the pedal, the air pressure in the system drops quickly. At that moment, an often overlooked quick-release valve comes into action. It expels the air from the brake chamber directly into the atmosphere instead of letting it slowly return through the lines. This allows the brakes to release much faster, with a quicker and more decisive response. Because the entire system relies on compressed air, before a heavy truck sets off, the driver usually starts the engine early. This gives the compressor time to build up pressure in the air tanks to above 0.6 megapascals. Only then is the entire air brake system fully operational and ready to go. I've always been curious about how exactly waves generate electricity. 70% of the Earth's surface is ocean, and waves crash against hundreds of thousands of kilometers of coastline worldwide every single day without stopping. That's such an enormous amount of free energy, yet humans still haven't fully turned waves into electricity. The earliest solutions were actually quite straightforward. Engineers would place two huge circular buoys on the sea surface, each nearly 10 meters in diameter, connected in the middle by 2 meter-long mechanical arms. When the waves came, the two buoys would bob up and down, pulling on the mechanical arms and activating the internal hydraulic system. This converted the up and down motion into high-pressure fluid, which spun turbines at high speed, generating electricity just like that. The whole process involved no burning and no emissions whatsoever. The only fuel was the waves themselves. Sounds pretty perfect, right? But the power of waves is truly terrifying. In calm weather, it sways gently like a cradle, but once a storm hits, the impact force of dozens or hundreds of tons smashes down on the device again and again like a hammer. Those massive buoys have to endure this pounding day after day, year after year. Over time, this kind of impact causes metal fatigue and corrosion, mechanical wear and tear. Maintenance costs become frighteningly high. Before long, repair costs exceed the value of the electricity produced. That's when second-generation devices started appearing. This time, engineers changed their thinking. They built a device that looks like a giant wine bottle at sea, 19 meters long in total, firmly anchored to the seabed with steel cables. When waves pass by, the entire body sways up and down with the waves, and internal gears spin continuously to generate electricity. But the truly clever part of this device isn't the power generation itself. It's the active adjustment system inside. It can sense the rhythm of the waves in real time and actively amplify its own up and down motion to squeeze out as much energy as possible from every single wave, instead of passively going with the flow. The power generation problem was solved. But how do you get the electricity back to land? These devices are often very far from the coast. Undersea cables are not only expensive, they also get corroded by seawater, pulled by strong undercurrents, or even snapped by ship anchors. Often the electricity hasn't even reached shore yet before the costs have already become ridiculously high. That's also why wave power research has gone on for nearly 100 years, yet it has been difficult to scale up widely. But just when many people were about to give up, engineers at one company suddenly realized, why do we always try to fight against the waves? Why not move with the waves like fish do? So they developed a completely different kind of flexible wave power device. This device looks just like a giant spine floating on the sea surface, made of many connected floating modules. Each section can bend freely. When waves come, it doesn't resist head-on. Instead, like a snake or a fish, it twists and turns continuously with the waves. Thanks to this soft overcomes hard approach, the device's lifespan has been greatly extended, and energy conversion efficiency has also improved significantly. Even more importantly, many parts can be made directly from ordinary plastic or even recycled waste plastic, without needing complex production lines. Manufacturing costs have been driven extremely low. According to currently published data, a single-wave linear magnet unit under ideal conditions can output up to 100 megawatts of electricity, and generation costs have started to approach those of traditional fossil fuels. Just last year, this device underwent its first real sea trial in Larnaca Bay, Cyprus, and the stability was even better than expected. Of course, besides wave power, humans are also advancing tidal power generation at the same time. Waves are created by the wind, while tides are pulled by the moon's gravity. Its biggest advantage is stability. You can predict exactly when high tide and low tide will occur, almost to the minute every day. The logic of tidal power is more like building a dam at sea. A barrage is constructed at the bay's outlet. During high tide, seawater rushes in to spin the turbines. During low tide, water flows out and spins them again. Electricity is generated both ways. France's La Rance tidal power station has been operating stably for nearly 60 years and to this day remains one of the world's most successful tidal power stations. Now, looking back at the whole story, humans spent nearly 100 years struggling on the path of wave power generation. The real problem was never a lack of energy. It was that humans kept trying to conquer the waves. Only later did we slowly realize that facing the ocean, the smartest way was never to fight it head-on, but to go with the flow, like water itself. So what do you think? If one day the entire ocean were covered with these flexible power devices, would humanity still face electricity shortages? Would we ever run out of power? I always thought that you could simply press it a bit to turn it into a steel plate. Until I delved deep into researching the hot rolling and cold rolling processes, I realized that the intricacies involved are far more complex than I imagined. Molten steel is just poured out from its liquid state at over 1,000 degrees Celsius. Before it even has time to cool, it is sent directly into the continuous casting machine. Here, it is rapidly shaped into slabs of standard sizes. Then, giant bridge cranes lift them up and send them into the heating furnace. As soon as the furnace closes, the temperature skyrockets to 1,100, 1,200 degrees Celsius. But heating alone isn't enough. At such high temperatures, a thick, hard layer of oxide scale forms on the surface of the steel slab. If left untreated, all the steel products rolled later will have defects. That's why high-pressure water treatment is essential next. Water at hundreds of atmospheres of pressure is sprayed instantly from multiple directions onto the slab surface, completely stripping away this oxide layer. This step is absolutely critical. It's like giving the steel a thorough deep clean that directly determines the final surface quality of the product. Once cleaned, the real rolling begins. First comes the rough rolling stage. A 225 millimeter thick steel slab is fed into the massive roughing mill. It is rolled pass after pass. With each stand it passes through, a layer of thickness is forcefully reduced. After 5 to 7 continuous passes, it goes from over 20 centimeters thick down to just 3 to 4 centimeters. But this is only the first step. Next comes the finishing rolling stage. The slab is now sent into a 6-stand continuous finishing mill for high-speed, stable rolling. Each stand fine-tunes the thickness and controls the shape. The tolerance is kept within an extremely tight range. At the same time, the system continuously monitors thickness, width, and even surface condition in real time. If any deviation is detected, the mill automatically adjusts immediately. This step determines whether this steel coil becomes ordinary material or a high-end premium product. But what truly determines its performance is not the rolling itself, but the cooling process that follows. After being shaped at high temperature, the steel undergoes precisely controlled cooling according to different process requirements. Some sections cool rapidly, others cool slowly. These different cooling rates alter the internal microstructure of the steel. Finally comes coiling. The long steel strip, tens or even hundreds of meters in length, is coiled at high speed into a tight, neat steel coil. It is then bundled and labeled. Each coil is weighed, and all its data is recorded. From molten steel to finished product, every single step can be traced back. Only then does a raw steel slab finally become a marketable industrial material. Besides this high-temperature hot rolling process, there is also the completely opposite cold rolling process. Cold rolling is performed under extreme pressure and high-speed friction to press the steel thinner and flatter without damaging the hot-rolled coil. The steel strip is fed to the start of the production line and slowly unwound. Before entering the rolling mill, the strip is thoroughly cleaned to remove all surface oxide scale and oil stains. Because even the smallest impurity will be magnified infinitely in later stages. After cleaning, the strip is sent into the cold rolling mill. Two high-speed rotating rolls, like two giant steel jaws, bite down hard on it. In that instant, the pressure reaches its maximum. The force per square centimeter can reach hundreds of tons. Meanwhile, the steel strip continues moving at high speed hundreds of meters per minute, even up to 1,000 meters per minute. But simply pressing hard would scratch and tear the steel. That's why an oil-water emulsion is continuously sprayed between the strip and the rolls, forming an invisible protective film that separates the steel from the rolls. As rolling continues, the strip gets thinner and thinner from several millimeters down to precision-thin strips. Finally, when the strip exits the last rolling stand, it becomes thinner, stronger, and smoother, with dimensional accuracy controlled down to the micron level. So the cold rolling you see is far more than just pressing steel. I always thought that pile drivers only rely on their own weight of over 10 tons to slowly drive the piles into the ground one blow at a time. Until I actually watched the working process of the pile driver, I realized I had thought too simply. What it really relies on is the enormous impact force generated by the high-speed falling hammer, driving the pile forcefully into the ground. The entire pile driver is actually an independent device. At the very top is the upper beam structure, which is responsible for supporting the main body of the entire equipment. The huge iron block in the middle is the hammerhead. It is the core component of the pile driver, usually weighing around 10 tons. The bottom of the hammerhead is connected to a steel cap, and on both sides are long guide rods. These guide rods act like tracks, restricting the hammerhead to only move up and down without swaying left or right. Ladders are installed around the entire upper beam structure for maintenance personnel to climb up when needed to inspect and repair the equipment. The raising and lowering of the entire structure is completed by the pulley system and the crane. In other words, the pile driver itself has no mobility. All its hoisting actions are actually powered by the nearby crane. Before the piling work begins, the pile must first be erected upright. The crane will vertically lift the huge concrete pile and then slowly place it at the designated position on the ground. Next, a pile cap is installed on top of the pile. This pile cap is very important. It acts like a cushion, evenly transmitting the hammerhead's impact force to the entire pile, preventing the pile head from being directly smashed. After the preparation work is completed, the next step is to lift the hammerhead. The hook on the base frame will lock the hammerhead. Then, through the pulley system, this 10-ton iron block is gradually pulled up into the air. When the hammerhead rises to the appropriate height, the nearby lever mechanism is triggered. The hook is instantly released. The hammerhead falls freely under gravity. With a loud boom in the next second, the iron hammer slams heavily onto the pile cap. The enormous impact force is instantly transmitted to the pile body, driving the pile bit by bit into the ground. However, each time the hammerhead can only be hooked manually. After each blow, the hammerhead must be hoisted up again and released once more. This efficiency is too low. So engineers placed a sealed cylinder in the center of the hammerhead. On the other side of the cylinder is a piston, and at the center position of the piston, a fuel injector is installed. Next to it is an oil pipe connected to a fuel pump. When the fuel pump operates, diesel is high pressure injected into the cylinder interior. So how does this fuel pump work? Inside the fuel tank, you can see that the fuel pump is actually immersed in diesel. On both sides of the pump body, a one-way valve is installed. This type of valve only allows fuel to flow in one direction. Under the action of the spring, these two valves are normally closed. When the fuel pump's piston moves upward, negative pressure forms inside the pump chamber. At this time, the left one-way valve is sucked open, while the right valve remains closed. Diesel is then sucked from the tank into the pump body. Next, when the piston compresses downward, the situation reverses. The pressure inside the pump chamber rises rapidly. The left valve is pressed tightly closed, while the right valve is pushed open. Thus, the diesel in the pump is squeezed out and eventually enters the fuel injector through the oil pipe. In this way, the fuel pump can continuously deliver diesel into the cylinder. Next is the most critical step of the entire diesel pile driver. After the hammerhead is released, it will fall at high speed under gravity. As the hammerhead descends, the piston inside the cylinder also moves downward together. Since the cylinder is completely sealed, the air has nowhere to escape and can only be continuously compressed. The more severely the air is compressed, the higher the temperature becomes. When compression reaches its limit, the temperature inside the cylinder can reach 250 to 300 degrees Celsius. The auto-ignition temperature of diesel is approximately 210 degrees Celsius. That means at this moment, as long as a little diesel is sprayed inside, it will automatically ignite. At the very instant the piston reaches its lowest point, the injector suddenly opens. A burst of diesel is sprayed into the high-temperature air. In the next second, the diesel instantly auto-ignites. The high-temperature gases produced expand rapidly, with temperatures even soaring to 600 to 700 degrees Celsius. Huge pressure instantly erupts inside the cylinder. This force violently pushes the piston and hammerhead upward. The iron block that had just fallen is thus pushed back into the air. Many people are curious why combustion can produce such great force. We can make a simple analogy. When a pot of water is heated to boiling, it turns into steam. If 1 liter of water is completely turned into steam, under normal pressure it requires approximately 1,700 liters of space. In other words, when a small amount of liquid turns into gas, its volume expands thousands of times. If these gases are confined in a very small space, the pressure inside becomes extremely terrifying. The gas expansion produced by diesel combustion follows the same principle. When the hammerhead is pushed to the highest point, the exhaust port on the side of the cylinder opens. High-temperature exhaust gases are ejected at high speed from the exhaust port. After the gases are expelled, a brief negative pressure forms inside the cylinder, so fresh air from outside is quickly sucked in. In the next second, the hammerhead falls again under gravity. The air is compressed again. Diesel is injected again. Combustion occurs again. This process repeats continuously. The machine can complete 50 to 60 hammer blows per minute, driving the pile bit by bit into the ground. So how is the timing of fuel injection controlled? The answer is right next to it, this small curved arm mechanism. A hook is connected to the hammerhead. When the hammerhead falls to a specific position, this hook touches the curved arm. After the curved arm is pushed, it presses down the fuel pump. Diesel is pumped out and sprayed into the cylinder through the injector. In this way, every time the hammerhead falls, it automatically triggers fuel injection. If the machine needs to stop, what to do? The method is very simple. There is a control lever here. During normal operation, this lever is held in the right position by the spring. When the hammerhead falls, it can touch the curved arm, thereby triggering fuel injection. But if you flip the control lever to the left, the position of the curved arm changes. In this way, when the hammerhead falls, it won't touch the fuel pump. Without fuel injection, there is no combustion. The hammerhead won't rise, and the machine naturally stops. If you peel back the glass curtain walls of the Burj Khalifa, you can see its internal structure is like a beehive. This highly concentrated vertical city can accommodate up to 35,000 people living and working inside at the same time. When the outdoor temperature often exceeds 40 degrees Celsius, Maintaining a comfortable temperature in such a super high-rise with air conditioning alone isn't enough. The real key lies in a massive water circulation system. Like in present-day Dubai, which mainly relies on large seawater desalination plants to supply fresh water. But to pump water up to over 800 meters high, this has pushed the physical limits of pumping. Because the building is extremely tall, if you pump directly from the ground with high pressure, the pipes would have to withstand enormous physical pressure and might even burst. To solve the pressure problem, engineers use a staged pumping approach. Fresh water is first pumped to reservoirs on the 40th floor. Then, through a network of giant water tanks distributed across different floors, it is sent to the top of the building. Once the water reaches the top, it uses gravitational potential energy to naturally flow through the pipe network to all floors. Just the Burj Khalifa alone consumes up to 750,000 liters of water per day. Across all of Dubai, inside more than 200 skyscrapers, there is a water supply network spanning thousands of kilometers. To isolate from the extreme surface heat, these pipes are all buried deep under thick layers of sand. Every minute, millions of liters of fresh water circulate through the network to meet the daily water needs of residents. Maintaining such super high rises requires complex water supply systems. And supporting these structures weighing hundreds of thousands of tons is an engineering miracle buried deep underground. In Dubai's most bustling commercial district, skyscrapers are packed extremely densely, each weighing an average of 250,000 tons. But beneath these buildings lies nothing but loose sand. The core challenge for engineers is preventing these massive buildings from sinking or toppling on the sand. In other cities with better geology, hard rock layers are usually found close to the surface, just a few meters down. But in Dubai, even digging 30 meters deep from the surface, you still hit soft sand layers which cannot support the weight of tall buildings. So to secure the foundation, engineers must drill through 35 meters of sand. During drilling, they pump thick mud slurry into the holes to use the pressure to hold up the walls and prevent sand collapse. Then they lower steel reinforcement cages tens of meters long into the holes and pour hundreds of tons of concrete. Once hardened, it forms solid columns known as foundation piles. In other cities, supporting a building of this size might require only dozens of piles. But in Dubai, 250 piles are needed. These piles extend nearly 40 meters underground. Through friction with the surrounding sand layers and support at the base, they firmly anchor the entire building. As the city continues to expand, engineers have built an incredibly dense foundation system underground in Dubai. In the city center, beneath the main roads, the amount of concrete used is greater than anywhere else in the world. Without these deeply buried supports, Dubai's skyscrapers could never stand firm in this sea of sand. Besides the shifting sands below, the towering buildings must also withstand fierce winds. As height increases, powerful winds become a major threat to structural stability. If a building has a too regular shape, airflow can create powerful vortices behind it, generating dangerous lateral suction forces. The core of the Burj Khalifa's design is to disrupt the airflow. It uses an asymmetrical, stepped profile with varying cross-sections at different heights. This design breaks up the airflow, preventing the formation of vortices, greatly reducing the building's sway. When dealing with direct wind pressure, engineers have other solutions too. Take Dubai's Burj Al Arab, the Sail Hotel, for example. The strong winds from the Gulf exert enormous pressure, enough to bend the building's concrete core. To address this, engineers installed a robust steel exoskeleton securely attached to the main steel structure. This exoskeleton effectively disperses wind forces, stabilizing the building's core. The structure also contains internal dampers which can move in the opposite direction to counteract wind-induced sway, ensuring a stable and comfortable indoor environment. It is these precise yet bold engineering solutions that have allowed Dubai to create architectural wonders on barren land.
Every time the president sets out, just how extravagant is his full motorcade? Pay attention. There are 50 specialized vehicles and more than 100 personnel who will all spring into action. But this is only the visible scale. What you can't see is what really makes your scalp tingle. At the very front are the route survey cars and sweeping motorcycles, which often leave before the president to scout and clear the entire route ahead. Right behind them, the vehicles have antennas densely packed on their roofs. As soon as they move, they start blasting full-band powerful jamming signals. All remote-controlled detonators within range instantly go dead, so even if there are bombs buried by the roadside, it's useless because pressing the button does absolutely nothing. Further back, several identical beasts roll along at the same time, constantly switching positions, so no one knows which one the president is actually riding in. Sometimes even his own people don't know. Also, in the vehicles right next to the beast are the elite operators selected from Delta Force and Navy SEALs, the best of the best, providing full protection the entire way. Behind them are hazardous materials detection vehicles. Their sensors can detect a single drop of liquid diluted across 20 standard swimming pools and still trigger an immediate alarm. And there's more. The entire motorcade can be fully sealed in just 2 seconds while maintaining a constant speed of 72 kilometers per hour. The spacing between vehicles has an error of no more than 60 centimeters. Helicopters overhead also monitor the entire journey. One more thing. The motorcade usually won't stay on the road for more than 30 minutes, because the longer it stays out, the easier it is to detect patterns. So this isn't just going out at all. It's clearly a full-scale mobile battlefield rehearsal that has to be practiced from scratch every single time.
This is the one that can easily swallow a whole bus, the C-5 Super Galaxy, the ultimate strategic airlifter. Its fuselage is nearly as long as a football field, and its height is equivalent to a 6-story building. As for its nose, it can flip the entire front half of the plane upwards as a whole. The mouth opens nearly 6 meters wide and 4 meters high, so a bus can drive right in with plenty of room to spare, haha. But just having a big mouth isn't enough, because the cargo hold sits about 3 meters off the ground, plus the ramp angle is way too steep. A tank weighing dozens of tons can easily slide back when driving up. So what do? This thing can actually kneel. It uses a hydraulic system to lower the entire aircraft. The nose landing gear retracts very deep, and the whole plane bows forward like it's doing a bow. And the ramp instantly flattens out. This way, the tank can drive straight in smoothly. The cargo hold is 37 meters long inside. It can carry 2 1 Abrams tanks and 6 helicopters. Its total payload is equivalent to 23 adult African elephants. Loading and unloading is super convenient. Vehicles can enter from the front and exit from the rear. As early as the Vietnam War, tanks drove straight through the plane and right onto the battlefield. Now let's talk about its complex internal structure. This aircraft actually has a double-deck design. The lower deck is the main cargo hold, while the upper deck is a complete living and working area. At the very front is the cockpit. Right next to it is a 2-level crew rest area with beds perfect for rotating shifts on long flights. Further back is the troop compartment. It can seat up to 75 soldiers facing rearward, complete with kitchen and restrooms. It's basically a flying mobile military camp. At the very rear of the troop compartment, there's also a reserve space called the Gan Sao loft. And at the front of this loft, there's a hidden dedicated ladder. Climb up along it, and you can go straight into the tall tail. There's a hidden maintenance walkway inside, but it's strictly off-limits in normal operations. It's only for ground crew mechanics during daily inspections. Now let's talk about the cockpit. The captain's position is a full 3 stories high. Because when the nose opens upwards, there has to be space, otherwise the pilots would be hanging upside down in mid-air. So the crew isn't just the pilot and co-pilot. There's also a dedicated flight engineer, specially responsible for managing fuel among the 12 tanks. As fuel burns off, the center of gravity shifts several centimeters every hour. So precise fuel balancing is extremely critical. At 10,000 meters altitude, if the ratio is off even a little, the nose could become too heavy or too light, with disastrous consequences, haha. When landing, all 28 wheels in 5 groups deploy at once, creating drag like deploying a giant parachute. The brake discs absorb so much energy, it's like stopping an entire freight train cold. Temperatures spike straight to 2,000 degrees Celsius, hot enough to melt aluminum. After touchdown, the cooling fans kick in like giant blow dryers and run at full blast for 45 minutes straight. Finally, the most important point, this plane doesn't picky about runways at all. Mud, grass, Arctic permafrost, it can take off and land anywhere as long as there's 1,500 meters of relatively flat area. This incredible versatility is exactly why 3 companies that tried to build replacements all failed spectacularly. The US Air Force invested $10 billion to re-engine it, upgrade the cockpit, and reinforce the wings just to keep it flying until 2040. So yeah, this plane is cooler and smarter than most pilots, and no other aircraft has ever been able to replace it. Haha. That's the legendary C-5 Super Galaxy.